Morning students. Today in this class we are going to see the Shannon Fano Coding Learning the communication engineering subject in a easier way. Contents. The topic we are going to discuss here is the Shannon Fano coding technique. Learning outcomes. At the end of the session, students will be able to know to encode the message of the transmitter using Shannon Fano coding technique. Need for Shannon Fano coding technique. If probabilities of occurrence of all the message are not equally likely, then average information is reduced, that is entropy H of X, which in turn reduces the information rate capital R of the transmitting system. This problem can be solved by encoding the message M with different length of code word bits. Shannon Fano coding is used to encode the message M depending on their probabilities. This algorithm allows less number of bits for higher probability messages, where this algorithm also allows more number of bits for rarely occurring messages, that is, it will assign less for less probability messages. An efficient code word can be obtained by the simple procedure given below. That is, right now we are going to see the Shannon Fano coding algorithm. As in Huffman coding, we are going to arrange the messages or the given symbol in order of their decreasing probabilities. Then partition the set of messages into two equiprobabilities. That is, the partition is made such that the sum of probabilities in both the set are almost equal. Assign logic 0 to the messages in the first subset and logic 1 to message in the second subset. Partition the subset again into two equiprobability subsets and assign logic 0 and logic 1 respectively. Repeat this partitioning until each subset contains only a single message or symbol. Right now we will solve the Shannon Fano coding with a problem. Construct a Shannon Fano coding for the following 5 messages: M1, M2, M3, M4 and M5 of a discrete memoryless source. Their probabilities are 0.4, 0.2, 0.1, 0.2 and 0.1. First, as given in the step, the messages are written in its decremental order in P. Next, we form the Shannon Fano coding table. Here, the probabilities of the messages are written in its decreasing order of value. In this, we are going to draw a dotted line. A pink color dotted line is drawn and a partition is made where an equal probability is being taken over here. Here, the first subset is going to have a probability of 0.6 and the second, the lower subset you called as an, will be having a probability of 0.4, which is to be a more or less equiprobable value. In the first stage, we will be assigning logic 0 for it and logic 1 for the lower subset. Then, as I am going to have two values, the process will be continued where the 0.4 and 0.2 is being again divided in equiprobabilities. So in stage 2, it will be having logic 0 in the upper subset and logic 1 in the lower subset. As we had arrived to a single value, the probability for 0.4 gets stopped here, and that's it is being written as stop. Next, in the stage 1, we'll be having 3 more probabilities, that is 0.2, 0.1 and then 0.1, where these equal probabilities are being searched for it, where that is being highlighted with the help of green dotted lines. So this green dotted lines is nothing but a mark of an equiprobable value, and in stage 2 we had written a logical 0 in the upper subset and a logical 1 in the lower subset. So therefore M4 is marked as 1 and M5 is marked as 1 in stage 2. Next, as I encountered logic 0, the M3 message stops. Only you have an M4 and M5 having a probabilities of 0.1 and 0.1. At stage 2, it is being further divided in equal probabilities. At stage 3, we will be having a logic 0 and a logic 1 in the upper and lower half. As we have encountered a single message, the division is stopped at this point. In the next column, we had written the code word for the Shannon Fano coding. Here, obtaining the code word for the Shannon Fano coding is very easy. That is, just we are going to add up or concatenate what and all the logical values that have been given in stage 1, stage 2, stage 3. For example, for a message M1 of probability having a probability value of 0.4, in stage 1 I have a logical 0, in stage 2 I have a logical 0, that is being written as a code word logic 0 and 0. We'll take another harder example, that is M5. M5 that is having a probability of 0.1. In the stage 1 it has got a logical 1. In stage 2 it has got as a logical 1. In stage 3 it got a logical 1, and all of them are being concatenated and it is being written as a code word, where the length of the code word L of k, small l of k, is nothing but count of how many number of bits are being there in the code word. So we'll be having 2, 2, 2 and then 3, 3. The code word is obtained by reading the bits of a particular message row wise through all the columns. The message M1 has only 2 bits 0, 0, and the message M5 has 3 bits 1, 1, 1. The message M1 has the highest probability, hence it is encoded with 2 bits, whereas the message M5 having the lowest probability of occurrence and hence encoded with 3 bits 1, 1, 1. As probability goes on decreasing, the bits in the code word or the code word length increases. From this partition table, the code words are written in rows and the integer length of the code words are counted. And these are taken to the next process of determining the average code word length, capital L. So the capital L, the formula you are going to use is summation of k is equal to 0 to k minus of 1 open bracket p of k into L of k close it, where L is equal to 0.4 into 2, 0.2 into 2 plus 0.2 into 2, 0.1 into 3 plus 0.1 into 3. The value what you are going to get it at the end is 2.2 bits per symbol. Next, we will be finding the entropy of the Shannon Fano coding. For this, the formula you used is h of x is equal to minus of summation of k is equal to 0 to k minus of 1, probability of k into log to the base of 2 into p of k. As you know, log to the base of 2 is not possible to calculate it on a calculator. We are converting it to log base 10. For this conversion, 3.32 is being taken, and then we'll be expanding it is to be of 0.4 log to the base of 10 into 0.4, and then 0.2 log to the base of 10 of 0.2, and it's extend for the all 5 probabilities. Thus, we'll be determining the answer to be of h of x equal to 2.121 bits per symbol. Thus, how we'll be determining the entropy of the Shannon Fano coding algorithm. Next, we came to the end of the coding algorithm, that is determining the coding efficiency eta. So coding efficiency eta is going to have a standard formula, that is entropy divided by average code word length, that is h of x divided by L. Thus efficiency is equal to 0.964 and percentage efficiency is nothing but 96.4%. So we'll be having a maximum efficiency in the Shannon Fano coding algorithm, but this efficiency is to be less when compared to that of your Huffman coding. This is how in a transmitter end we used to convert the given statistics into your bits or the code words. The Shannon Fano coding resource material or the reference is taken from the communication theory, Saminakin's book. Thank you, students. We'll join in the next topic of communication engineering. Thank you.